Welcome back to Wood Engineering. I'm Jeff Orochko from Carleton University, and in this video, we're going to do an example calculation for parallel to grain built-up column resistance. So we're talking about columns that are not made of a single member, but are made of multiple members, all stuck together. So in this case, we're looking at 4 different members stuck together, and they're all connected using either bolts or nails or split ring connectors. And we've looked at in a previous video how to calculate the resistance of these for bolted and nailed connections. So in this particular problem, we have 4 38 by 140 lumber sections that we are putting together in order to make a single big built up column section. And we're trying to calculate what is the axial strength of this column in compression. And the axial strength of the column is the parallel to grain strength of the column. We are assuming that this column is 1.9 meters. Well, the column is 1.9 meters long, so not very long. Pinned at both ends. So we have a pin at the bottom and a pin at the top. So we have basically simple support for this column. It's going to bend in a K=1 type of buckling shape. It has in a wet service condition and preservative treated unincised. So that will tell us our KS and KT factors. And we're going to compare what is the strength of this column if I do it as a built-up section or if I do it as a section that is just basically 4 individual members which happen to be sitting right in the same place. So the first thing that we're going to do is to determine all of our modification factors and determine our strengths, which come from the tables in the standard. So it already says here that we are assuming a standard load duration. So that means that KD equals 1.0. Okay, in real life, of course, we would have probably multiple different load combinations here. So we would be calculating multiple different strengths, one for each associated load duration factor. As I mentioned before, in compression parallel design, we cannot do that thing that we did for tension design where we take the load combinations and divide them by KD to see which one governs. And that's because the KD factor comes in to the strength equation twice. And I'll point that out again when we get to it. So KD equals 1.0. This is wet, unincised. So if we go to our service condition factor, you'll see that we have here wet conditions for lumber of least dimension, and we're talking here about compression parallel to grain, KSC. We're also going to need this one down here, the modulus of elasticity, KS factor, when we do our KC calculation, which is the slenderness factor calculation. So we're going to need both of these. Which column here applies? Wet service condition sawn lumber piling and poles of least dimension, 89 or less or over 89. Well, we are dealing here with a dimension of 38 by 140. So the question here is, which one do I use? Do I use the one for the individual members or do I use the one for the built-up section? Well, the built-up section is only for calculating the strength. It does not change the calculation for service condition, because since these since this is not actually a solid member, water can get in between the different plies much more easily than it could get into the center of a solid member. So I think the correct approach here is to consider KSC for each individual ply, not for the whole built-up section. Of course, we're doing both calculations here, but so this isn't going to change. So let's go back to here. So if we're doing it for each individual ply, they're 38 by 140. So the least dimension is 89 or less. So that means my KSC is going to be 0.69 and my KSE is going to be 0.94. So let's put those in here. We have our KSC is equal to 0.69 and our KS capital E for our Young's modulus is 0.94. Okay, very good. So now we need our KT. which, if we go back to this table, we're talking about preservative treated unincised lumber. So for wet service conditions, that's 1.0. KT equals 1.0. And then our last one, KH, this is our system effect factor. And so you'll recall that for system effect, what is required is, for case 1, is that we basically have 3 or more members supporting the same load. It says, for case 1, if you recall, a system consisting of 3 or more essentially parallel members spaced not more than 6/10 apart and so arranged that they mutually support the applied load may be multiplied by system factor for case 1. And so that happens to be the case here because we have 4 members, which is more than 3. They're definitely spaced less than 6/10 apart because they're adjacent. So built up or no, for both cases, we have system effect factor case 1. So whether or not we consider this to be a built up section or 4 individual pieces mutually supporting the load, both cases should apply case 1. So that means for our case, for KH, we have case 1, compression parallel to grain is 1.10. 1.10. You may recall that case 2 is basically for systems of joists or wall systems that are held together with sheathing, and it has certain nail requirements. So that certainly doesn't apply here. So we're only talking basically about case 1. Okay, so now that we have those, let's go and find the strengths of our member for this particular size. So remember that our size is 38 by 140. Now make sure we're going to find the strengths of the actual pieces. Okay, so I have, 4 of these all stuck together. When I go to find my strength, whether I'm considering it as a built-up section or whether I'm not considering it as a built-up section, it's the strength of the ply that matters. Okay, so when I go to this visual grade and their dimensions table to figure out which grade category I'm in, it doesn't matter, for example, if I'm considering this thing to be a solid piece, that doesn't change the strength of the plies, right? So just because this is a bigger piece, that doesn't mean I go down here and say, oh, well, now I'm in the, post and timber grade category. No, no, no. Do not do that. Right? So it's the strength of the strength of the piece of wood is based on how it was graded, and how it was graded is based on each the size of each individual ply. Okay, so our plies happen to be 38 by 140, right? So that means smaller dimensions 38, so it's one of these 4. It's 140, so it's this one, and I believe it was number 1 grade. So we're basically talking about this category here, structural joist and plank. So that means I have to go to the structural joist and plank table, which it says here in table 6.3.1a. And this is where I'm going to pick out my, my compression strength and also my E and my E05 as necessary. Okay, so if you recall, we're talking about Douglas fir number 1. You see in the top right, it's 38 by 140, Douglas fir number 1. So back to our table, we're talking about Douglas fir, number 1. So we read across, parallel to grain strength is 14. My E05, which is the number I'm going to need, is 7,000. And my E, which I don't really need because I'm not calculating a deflection here, but I'll write it down anyway, is 11,000. So I'm talking about 14 MPa for parallel to grain compression strength, 7,000 for my E05. So let's go back and record those data down. Okay, so my FC is equal to 14.0 MPa, and my E05 is going to equal 7,000 MPa. And remember, we're using E05, that's our 5th percentile value for stiffness. That's a lower value of stiffness, and we're using that because that stiffness goes into the KC equation, which has a consequence on strength, not deflection. So since we're talking about strength, it's important that we use a conservative value. If we were trying to calculate a deflection, we'll just use the mean value because it's not something that's going to cause failure of our structure. Okay, so now we've got basically all of our input information, all of our modification factors, and all of our strengths. So now we can start going about to calculate all our different axial buckling strengths. But first, we might as well calculate capital FC, which we're going to use throughout. So always as well, phi is going to be 0.8 for compression parallel. And FC is still small fc, kd, kh, ksc, kt. And so we have 14.0 kd. We're talking about standard term 1.0, kh is 1.1, ksc is 0.69, and kt is 1.0. And so if we multiply that together, we get 10.6 MPa. So that's going to come into basically all of our calculations. Okay, so in this case, we have our buckling length, and we only have a single column, and that column is connected only at the tops. So for both directions, we have the same length, and we have the same effective length as well, because we have pin condition. So the effective length of this column happens to be the same as the actual total length, because we don't have any supports, you know, halfway up that are preventing buckling. So it's buckling from end to end, and it is a simple buckling shape, basically, that looks something like this, which means our K equals 1. So effective length, in this case, equals our length. So we might as well write that down too. So LE equals L times KL, right? Which in this case is 1.0 times our total L is 1.8 1.9 meters. So equals 1.9 meters for strong and weak axis buckling, sorry. So this situation is considerably more simple than the previous example that we did for glulam, where we had different buckling lengths for, different effective lengths for buckling for each direction. Okay, so first, let's do the case where we have adequate bolting. So we basically have a built-up section. Okay, so we're going to consider first that our section is adequately bolted, which means that we are matching the bolting requirements that we talked about in the previous video, where we talked about built-up sections. So that means that our spacing between the bolts is adequate, and also I have a correct number of rows, and I'm using at least 1/4 inch bolts. So we're assuming that that's all true. So I'm not going into right now the detailing of the bolted connection, but we're just assuming that it's true, that it's adequately bolted. So that means I can consider my built-up section as if it's just one solid section that is this whole outer size. And of course, in ours, we have 4 pieces all bolted together. Okay, so if we do that, we're going to look at both directions. Remember that for lumbar compression parallel, I have to check all the way through the calculation for both buckling directions. So for strong axis buckling and for weak axis buckling, I can't just check which one has the higher slenderness. And that's because of the size effect factor working in a counter effect to the slenderness factor. Okay, so as one gets small, the other one gets bigger. Okay, so if I want to calculate this, let's start by calculating our cross-sectional area, which, since we're considering this to be one big section, is 140 millimeters times 152 millimeters. And we come out with 21280 millimeters squared. Okay, and we can calculate our KZC. Okay, so sorry. So that's going to apply to all of the analyses. So now let's calculate our strong axis and weak axis separately. Let's start with the weak axis buckling. Okay, so just to be clear, when I'm talking about weak axis buckling here, I'm talking about the weak axis of the plies. Okay, because this is the one where we apply our reduction to. So I'm talking about buckling in that direction. So it's strong axis of the built-up section, actually, but it's weak axis of the plies. So that's the direction I'm talking about now, weak axis of the plies. Okay, so if I'm doing weak axis of the plies, I do K KZC for week. So when I do size effect for week, I need to consider this equation, 6.3 dl to the negative 0.13, right? Now, so this is another question, right? So since I'm doing size effect here, which d do I use? Now, obviously in this equation, I'm supposed to use the d for the weak axis direction. So it's the dimension in the weak axis direction. But since I'm doing a built-up column here, my d should be the weak axis direction of the individual ply. The reason being, because since this is a size effect factor, it's based on the size of the piece of lumber, right? Because this is, again, related to how grading and defects affect the total strength, right? So that doesn't change when I put a bunch of lumber pieces together, right? I'm not going to get a different strength of my individual member just because I've put a bunch of lumber pieces together. So it would actually be conservative to consider a larger size. So that's an approach, but I think it would still be appropriate here to use 6.3 times 38 times our L, which is 1900 millimeters to the negative 0.13. Okay, because this is size effect factor for the individual pieces. So then when I do this, I get 1.47. And this equation dictates that KZC has to be less than 1.3. So therefore, KZC equals 1.3. Okay, so we're talking about weak axis. Okay, so let's continue by doing weak axis slenderness and weak axis buckling. So CC weak here. And again, I'm talking about weak axis of the plies is going to be the length 1900 divided now by the total length of the solid section, because this is the primary benefit I get from doing my built up section, right? So since I've built this up, I get to use that total 152 when I calculate my slenderness. We are considering that this section is like one solid piece for the purposes of calculating slenderness. Okay, so that's what we're doing right now, is calculating slenderness. So now instead of I'm not using 38 here, I'm using 152. And I get a slenderness of 12.5. And I have to check that this is less than 50, which it is. Therefore, my design is okay so far. Okay, so now let's calculate our KC in the weak axis direction. Okay, I'm just going to sub in the values. We've seen this equation many times before. 1.0 plus 10.6 is our FC. 1.3 is our KZC. 12.5 is our slenderness. We cube that. Divided by 35 times E05 here, which is 7,000, times 0.94, which is our KSE. Service condition for Young's modulus, and then we put that all up to the -1 and we get 0.895. So now we can go back to our PRY equation, PR weak, and we get 0.8, that's our phi, 10.6. Actually, let's write that all out one time at least. We have phi times FC times A times our KZC times our KC. And then here we're going to add a 0.75 because it's bolted and we're doing it in the weak axis. So for our PR weak, we have to reduce it to 75% to account for the bolts not making a perfect connection between the bolt-up column members. So that's where we're putting in our 75% right there. And we only have to apply that to the weak axis direction, not to the strong axis direction. So the strong axis direction buckling is not affected by the connections between the members, as we learned when we talked about built-up columns. Okay, so this is 0.8 times capital FC, which is our 10.6, which we had before, times our area, millimeters squared, times 1.3, which is our KZC, times 0.895, which is our KC weak, times 0.75, which is our reduction to account for our built-up section, and we get 157.5 kilonewtons. Okay, so that's for our PR weak for our adequately connected bolted section. So you can see we have a pretty good strength. Okay, let's look at the strong axis of the plies. And we're going to go through the same process, which is calculate our KZC, which is different in the strong axis than the weak. That's different from the way that it is for glulam. For glulam, KZC, our size effect factor for compression, is the same for both directions because it's based on the volume of the member. So here it's based on which direction we're buckling in. So we had 38 for weak axis buckling, and we're going to have 140 for strong axis buckling. So let's calculate that again. So we have KZC strong equals 6.3 times 140 now, that's the change, times 1900, which is our length, all this to the negative 0.13. Remember again, these values have to be in millimeters, otherwise this one won't work. So for the lumber one, they have to be in millimeters. For the glulam one, the volume has to be in meters cubed, so be well aware. Okay, and here we get 1.242, which is less than 1.3, so that's the one that we're going to go with. Okay, then we go back and calculate our CC strong. So this is our slenderness, which is our length. This is our effective length, which happens to be the same as our length, divided by the direction, the dimension of the whole solid built-up piece in the strong axis. So if we go way back up here, you see that that direction is, this is the strong axis direction buckling, and the dimension in that direction is 140. So you can see that that doesn't change whether we consider this as a built-up section or not. So we're going to say 140 here, and we get a slenderness of 13.5, say 13.6, which is still less than 50. So it's okay. Okay, now we're going to go through the same process again at calculating KC for the strong direction, and we're going to do this big equation. And once we plug in all of those, the only things that changed were the KZC 1.242 and the CC, which was 13.57, and we get a KC for the strong direction of 0.875. Okay, so far so good. Now we can go back to our PR, and it's going to be this time phi FC A, then times the KZC, our size effect factor, and our KC, which is our slenderness factor. This time we do not put the 75% reduction because we're talking about strong axis bending, and the quality of how well the members are held together in the strong axis is not affected by the bolting. So basically we don't have any reduction for the strong axis, which we saw before when we learned about this at the beginning. So if I sub all these in, I get 0.8, so this is our strong axis buckling. So obviously between these two, we're in a pretty good shape. Like they're pretty similar, 157.5 and 196.1. And all that makes sense. It's about similar because we have a square-ish section. The weak axis one is a bit smaller than the strong axis one because we had to reduce it by the 75% to account for the bolted connections not being perfect. So the total strength of this column, PR, because this is PR strong, PR total is going to be the minimum of the two, which in this case was the weak axis, which is 157.5. This is for the built-up section. Bolted adequately. Okay, very good. So that's our final strength. Okay, so now let's go back and repeat this process if we have inadequate bolting. So here before we were doing adequately bolted, so now we're going to do inadequately bolted, and we are going to consider that each of these sections is basically an independent section, inadequately bolted. Okay, so in this case, since we're not considering it to be a built-up section, we're going to treat each member as if it's an individual piece, and we're going to calculate the strength basically of one member, and we're going to multiply that total strength by 4, since there happen to be 4 individual members in that location. So our KH of 1.1 that we assumed before still applies, but now our A, our cross-sectional area, is going to be just for a single ply. I mean, they're not really plies anymore because they're not connected. It's just for a single member, which is 38 by 140, which is 5320 millimeters squared. So let's start again with weak axis buckling. And now this truly is weak axis buckling because we're only looking at the one member, and it will buckle at a very low strength in its weak axis. Okay, so KZC for weak, in this case, is the same as it was before for weak axis buckling for the built-up section. Since this is a size effect, it doesn't get affected by building the section up. So 1.47 again, which is greater than 1.3. Therefore, KZC weak is 1.3. Very good. Okay, so we continue by calculating now the slenderness. So this is the primary place where we're losing all of our strength, because now we have to consider our slenderness for each individual member, and we're not considering it as a solid built-up member anymore. So we're just looking at the slenderness of basically a single 2x. So we have the total length divided by 38, which is the weak axis buckling direction. So if I go all the way back up to my diagram here, you can see each of these plies is 38. So I can, if I was looking at this, so since I'm just looking at one and I'm looking at buckling in this direction, my my dimension associated with buckling in that weak axis direction is just 38, okay, instead of 152. So 152 was much better. 38 is pretty bad. So that's what we're going to use. And when I do that calculation and I use 38, I get 50, which is less than or equal to 50. So it's okay. But basically, this is the most slender member that I could possibly ever design. Okay, that's why the length of this column is 1900 for this example, because it's basically just 38 times 50. Okay, so this is basically worst case slenderness. So let's go ahead and calculate what is our slenderness factor with this worst case slenderness. So here my slenderness, 50, is being cubed in this equation. So you can imagine that that is going to be a very big number. So we're going to have a very high slenderness effect. And when I multiply all this out, at the end, I get 0.118. So I've lost almost 90% of my strength in buckling. Okay, so that's not great. Okay, so when I calculate my PR weak here, okay, I'm going to do 4 times phi. So that's because I have 4 members. So if I want to get the total strength of all 4 members acting together, 4 times phi times FC times A times KZC times KC. I do not put a reduction here of 75% because I'm not considering that this is a built-up section. So I only put that 75 if I am adequately bolted and considering it as a solid built-up section. So this has nothing to do with built-up. This is just I'm doing 4 individual columns just all happen to be next to each other. So I get 4 times 0.8 times 10.6 is my FC. My A is 5320. That's just the area of each individual member, times 1.3 is my size effect, times 0.118 is my slenderness effect. And in the end, I get 27.7 kilonewtons. Much, much lower than what we had before. Okay, let's now do the strong axis for completeness sake. Okay, and for strong axis buckling now, I have the same A. So let's just calculate the KZC, which is going to be the same as it was before for strong axis buckling. I get 1.242, which is less than 1.3, so that's okay. And then when I calculate my slenderness for the strong axis direction, I get 1900 divided by 140, which is 13.57. That's the same as the value I got before for strong axis direction, because the strong axis buckling strength is not affected by the built-up section, as we've talked about now many times. So that number is the same. KC strong is also going to be exactly the same as it was before, which is 0.875, which was what it was for strong axis buckling before. So if I go up here to the strong axis buckling, when I calculated K, I had the same strength, 10.6, the same KZC, 1.242, the same CC, 13.57, and all the rest are the same. So I get the same KZC of 0.875. And now when I calculate my PR for strong axis buckling, I have 4 of them. So I have 4 times phi times FC times A. Now that's A of the individual element now, times KZC times KC. No reduction, but I didn't have a reduction before. So I get 4 times 0.8 times, 10.6 MPa times A is 5320. KZC is 1.242, and my KC is 0.875. And I multiply that out, and I get 196.1 kilonewtons, which happens to be exactly the same number that I got for strong axis buckling up here, 196 kilonewtons, right here. And that's because the only difference between these two equations ends up being that here I have the total area 21,280, which is 4 times the area that I'm using down here, which is 5320. So instead of that 4 being in the area, it's out here. Okay, so 4 times 5320 is the same as the total area that's used in the equation above. So these two equations end up being identical, and so I get the same strong axis buckling strength whether I consider the section to be built up or not, which we know to be the case. But the P total is now going to be the lower of the strong axis and the weak axis buckling, which is obviously the weak axis buckling in this case, which is 27.7 kilonewtons when no adequate built-up column connection. So you can see how big of a difference it makes, because when we considered it to be a built-up column, the strength was 157.5. And now all that we've done is considered that I have not connected these together properly, and my strength has gone down to 27.7. So the built-up column makes a huge difference. So that's the end of this example. Hopefully you've seen the effect of built-up columns. And the other big takeaway is that the strong axis buckling is not affected by whether we consider the column to be built up or not.